Today we shall be looking at Bernoulli's equation.
Bernoulli's equation. Now, in Bernoulli's equation,
it takes a leap from the fundamental basis of linear first-order differential equation, and we use the application of the first-order linear differential equation to solve Bernoulli's problem. If, for example, we are given a question x y prime minus s cubed y squared plus 4y equal to 0. Assuming you are given this question and you are expected to solve it based on Bernoulli's relationship or general solution expression. Now, the concept of Bernoulli's has a lot to do with rearrangement of the question before solving it. So we now have x y prime plus 4y equal to s cubed y squared. This is the solution to the above problem. We shift minus s cubed y squared to the right hand side. Furthermore, we are going to divide all through by x to make y prime on a lone expression, a derivative expression. So we divide it by x, divided by x, divided by x. S go for x. Y prime therefore plus 4 over xy is equal to x squared y squared. By the time we divide through by x. Now, by implication, this is no longer a linear first-order equation, but a Bernoulli's equation because of the y squared here. So you divide through by y squared, and that gives us y raised to the power minus 2y prime plus 4 over x y minus 1. Now, simply because when you divide y by y squared, this is y raised to the power 1 minus 2 to give you y raised to the power minus 1 is equal to x squared. Now, based on Bernoulli's implication, we are meant to have a substitute for y raised to the power minus 1. So we can use vector z. Z is equal to y raised to the power minus 1. If z is equal to y raised to the power minus 1, it therefore means it will differentiate implicitly the z, the x is, based on differentiation relationship, is minus y minus 2 dy dx. Take note that if this is assumed as equation 1 and this is equation 2, and we have to substitute a relationship for minus y raised to the power minus 2 dy dx in equation 1, as this is almost a semblance relationship. So the only difference between this expression and this is minus 1. So multiply equation 1 by minus 1. When you multiply equation 1 by minus 1, we'll be having minus y raised to the power minus 2 dy dx, which is the y prime. Minus will multiply this to be minus 4 over x y raised to the power minus 1 is equal to minus x squared. We have multiplied through by minus 1. This equation, equation 3, was multiplied by minus 1. Take note. It was multiplied by minus 1. By minus 1. So comfortably, we can re-express this as a z format expression. It's a z function, which now gives you dz dx minus 4 over x z is equal to minus x. Now, this is equation 4. And this is a Bernoulli's expression. When we are to solve it, basically, in the line of linear first order differential equation, we utilize the linear fundamental expression. That is to say, this will now be z multiplied by exponential integral p dx equal to integral q multiplied by exponential integral p dx whole dx plus arbitrary c. Now, what actually transpires here is fundamentally based on the equation, the relationship. So as it stands, based on implication, the z value we have as a Bernoulli's expression is simply y raised to the power minus 1. But we will now use z exponential integral p. P becomes the value to represent the integrating factor, which is exponential p dx. Exponential p dx is the integrating factor. So the integrating factor becomes minus 4 over x differential x is equal to integral of q, the value at the right hand side. And the value at the right hand side gives us, the value at the right hand side simply gives us integral of q, and q is minus x. Q is the value at the right hand side. Q is the value at the right hand side. So that gives you, multiplied with the integrating factor, which is integral exponential integral of minus 4 over x differential x. Then you integrate it jointly. So with this connotation, it simply implies that this gives us a workable expression that can be aligned as z exponential minus 4 ln x, when we integrate this, is equal to minus integral x exponential minus 4 natural log of x differential x plus c. So that this gives us z multiplied by x raised to the power minus 4. Because exponent ln of a function is a function. So minus 4 will move here based on laws of logarithm to give you x raised to the power minus 4. So, but there is a law that exponent ln of a function, exponent ln f, is equal to f. Based on exponent ln of a function is a function, by the time minus 4 goes up here, it gives you x raised to the power minus 4. So it will now be, rather than exponent ln x raised to the power minus 4, it just gives you x raised to the power minus 4, because exponent ln of the function is a function, is equal to minus integral x. Exponent ln of the function is a function, dot x raised to the power minus 4 differential x plus c. This is exactly what transpired here. So it is a replica because it's an integrating factor. It appears here on the left-hand side and it appears on the right-hand side. Take notes. So that at the end of the day, we'll be having z dot 1 over x raised to the power 4 is equal to minus integral of reciprocal x raised to the power 3 differential x plus c, because this is x over x raised to the power 4 by reciprocal law. So this simply gives us this expression, because 1 over x raised to the power 4, x over x raised to the power 4 gives us 1 over x raised to the power 3. This is x over x raised to the power 4. So when you cancel out, you have it. So that z itself, ab initio, was given as equal to y raised to the power minus 1. That is z. If z is equal to y raised to the power minus 1, so we now have 1 over y x raised to the power 4. Because this is now y raised to the power minus 1. So this gives you 1 all over, because this is also at the denominator level, is equal to the integral of x raised to the power minus 3 will now be minus x raised to the power minus 3. Minus 3 plus 1 over minus 3 plus 1. So that will be minus 3 plus 1 is minus 2 over minus 2. Because if there is originally minus sign here, if you are integrating this reciprocal, it gives you minus 3 based on integration expression. Minus 3 plus 1 over minus 3 plus 1. So this gives you, so minus cancel minus 2. So that at the end of the day, arbitrary constant C is always a continual expression with respect to integration. Since it's in integration without lower and upper limits, this is an indefinite integral. So therefore, we progress to get 1 over y raised to the power 1 over y raised to the power 1 multiplied by x raised to the power 4. Or of course, you could multiply both sides by x raised to the power 4 if you wish. And by implication, x raised to the power 4 cancel x raised to the power 4. Then we relate this to give us x raised to the power 4 into this minus is gone based on this minus here because of the reciprocal 2 that appeared in the integration. So that at the end of the day, what we'll be having is a reciprocal of this, which is now giving us 1 over 2x squared plus arbitrary constant c. Of course, you could leave the answer that way or go further by multiplying through. You can multiply through by x raised to the power 4 to open the brackets. So at that level, it is also good you leave it this way. Yes, the rest is simplification. That is to open the bracket with x raised to the power 4 to multiply it, so you can now divide it. Same you do here with x raised to the power 4 multiply c. But of course, you could leave it this way or make y the subject formula. So fantastically, we have been able to resolve the Bernoulli's relationship by first looking at the separation of this value, this entity, to the right hand side, then dividing through by x variable to make this a lone expression. So we now have our integrating factor, which is 4 over x. That's it. Hence, the answer has appeared.